This video covers carboxylic acid derivatives, and the four most common derivatives that we're going to talk about in this video and the next video are shown here. The acid halide, so that's where you have a halogen where you, in the carboxylic acid, had an OH group. There's the acid anhydride, where you have this group shown in red, so an oxygen connected to a carbonyl connected to an R group. There is the ester, where you have an OR group instead of an OH, and then the amide, where you have a nitrogen instead of the OH. And the nitrogen could have two hydrogens, one hydrogen and an R group, or two R groups. This with two hydrogen is called a primary amide. If the nitrogen had one R group, it would be a secondary amide, and if it had two, it would be a tertiary amide. So any compound where carbon has three bonds to an electronegative atom is called a carboxylic acid derivative. So technically a nitrile is also a carboxylic acid derivative. So here if we look at the acid halide, in this case it's an acid chloride, this carbon has two bonds to oxygen, which is electronegative, and one bond to chlorine, which is electronegative. So that's a total of three bonds to electronegative atoms. Acid halides and anhydrides are relatively unstable and are not common in naturally occurring compounds because they tend to react to form more stable things. However, esters and amides, in contrast, are very abundant in nature and are stable. So we have methyl butanoate, which has a pineapple smell, isopentyl acetate, which has a banana smell, and butyl acetate, which has a pear smell. And these are all examples of esters. Proteins are biomolecules that are composed of amide linkages. So here we have the amide functional group, and this protein consists of several of these amide linkages. And many other compounds also feature amides, such as melatonin, which is a sleep aid. To name an acid halide, you're going to replace the IC acid for the parent carboxylic acid with YL and then whatever the halide is. So if we had acetic acid to begin with and we replace the OH with the bromine atom, then the acetic becomes acetyl, and then we use the term bromide. Similarly, if we had benzoic acid as the parent carboxylic acid and we swap out the OH group for the chlorine, we take that IC at the end of benzoic and we replace it with a YL, and we replace the word acid with chloride, and this becomes benzoyl chloride. If you have an acid chloride connected to a ring like cyclohexane, with the parent acid this would have been called cyclohexane carboxylic acid. For the acid halide derivative, that becomes cyclohexane carbonyl chloride. To name anhydrides, we replace the acid name of the parent carboxylic acid with the word anhydride. So here we started with acetic acid, and now we're going to have acetic anhydride. Succinic acid becomes succinic anhydride. Notice what we've done here is we've essentially connected two acetic acids to form the anhydride. So since these carboxylic acids are on the ends of the same molecule, they would form a ring in the corresponding anhydride. If you have asymmetrical anhydrides, so the group here is different from the group on the right, then you're going to list the acids alphabetically followed by the word anhydride. So the acid corresponding to what I drew in red would be acetic acid. The acid portion circled on the left would be benzoic acid. So when you take those two and you put them in alphabetical order, it becomes acetic benzoic anhydride. And in the course of making an anhydride, you will lose an oxygen atom because notice there's just one oxygen atom, not two oxygen atoms. To name esters, you start with the name of the group attached to the oxygen. So this is an ethyl group, so you start with ethyl, And then you look at the rest of the molecule and identify what that carboxylic acid's name would be, but change the suffix to ATE. So this molecule would have come from acetic acid, the parent acid, so that becomes ethyl acetate. We took off the IC and the acid and we replaced it with ATE. Here, if we have malonic acid and we change that by adding ethyl groups to each oxygen, then that becomes diethyl malonate. So notice we replaced what's in red here, the IC acid, with ATE. And then the same rules apply if the ester is connected to a ring. So notice here we have a methyl group attached to the oxygen, so methyl is going to come first. And then the rest of this, we think about the parent acid, what it would have been called, which would be cyclohexane carboxylic acid. And we change that by making it cyclohexane carboxylate. So again, we're removing the IC acid and adding ATE. To name amides, we replace the IC acid suffix or the OIC acid suffix with amide. So if we have this amide, that came from the parent acetic acid, so we take off the IC and the acid and we add the suffix amide, and that becomes acid amide. Same thing here for benzoic acid. If we want to switch this out and have a nitrogen, that becomes benzamide. So you take off the OIC and the acid and replace that with amide. If the amide group's connected to a ring, then you simply replace the carboxylic acid term with carboxamide. Now, sometimes the nitrogen of the amide group will have alkyl substituents on it. Sometimes it will just have hydrogens. If there is an alkyl substituent, you need to indicate that when you're naming it. So, for example, if we just have one alkyl group, like a methyl, you would indicate that at the beginning by saying N, capital N and italicized, methyl acid amide. And if you had two of them, it would be N-dimethyl acid amide. To name nitriles, you want to replace the suffix ic acid or oic acid with o-nitrile. So, for example, acetic acid becomes acetonitrile. This carbon maps onto that carbon. And benzoic acid becomes benzonitrile. That carbon maps onto that carbon. This shows the reactivity of carboxylic acid derivatives. The most reactive are the acid halides, for example, acid chloride, followed by the anhydrides, followed by the esters, and then your amides are your least reactive. And reactivity is determined by induction, resonance, sterics, and the quality of the leaving group. An important thing to know in figuring out the types of reactions that carboxylic acid derivatives can do is that you can convert a more reactive acid derivative into a less reactive acid derivative, but you can't go the other direction. So, for example, it's easy to convert an acid chloride into an anhydride, into an ester, and into an amide, but you cannot, at least not in one step, take an amide directly to the more reactive acid chloride or ester or anhydride, which follows our intuitive principles that it's favored to go from something more reactive to something less reactive. So acid chlorides are really reactive because of induction and resonance. So you have this really electronegative chlorine that is enhancing the electrophilic character of the carbonyl. So it's making this carbon even more partially positive, which makes it easy to be attacked by nucleophiles. Now with resonance, the chlorine atom does not donate much electron density to the carbonyl carbon, which also makes the carbonyl carbon more reactive. So this resonance structure here, where you don't have a positive charge on that carbon, is not a significant contributor. Amides are the least reactive, and if we look at induction and resonance, we can figure out why. First of all, the nitrogen atom is less electronegative than chlorine or oxygen. And then with resonance, the nitrogen atom does contribute significant electron density. So this resonance structure, where there's not a positive charge on that carbon, is a significant contributor. Carboxylic acid derivatives undergo reactions that are generically termed nucleophilic acyl substitution. So with aldehydes and ketones, these are electrophilic, but they do not undergo nucleophilic acyl substitution. And that's because the group here with a carboxylic acid derivative can function as a leaving group, whereas with aldehydes and ketones, the hydrogen or the R group could not function as a leaving group. And with this type of reaction, essentially what you're going to have is a nucleophile replacing the Z group here of your carboxylic acid derivative. The general mechanism has two core steps. The first step is that the nucleophile attacks the carbonyl carbon. So we've seen this type of step before. And then in the second step, you get the loss of a leaving group, which in this case is the Z group of your carboxylic acid derivative. And now you have a new product. So in this, the nucleophile attacks and you form what's called a tetrahedral intermediate because this carbon is tetrahedral. It has 4 groups attached to it. And then the carbonyl reforms itself while expelling the Z group. So here's an example. We could react an acid chloride with methoxide. So in this, the methoxide's a nucleophile. It attacks the carbonyl carbon, breaking the pi bond and creating a third lone pair on the oxygen atom here. And then since chloride is a better leaving group than OMe, that lone pair comes back down and kicks off chloride to form your ester. So here we've taken an acid chloride and converted it into the less reactive ester. It's important to note that nucleophilic acyl substitution is not an SN2 reaction. So here you cannot, this would be wrong if you showed the nucleophile attacking the carbonyl carbon and simultaneously kicking off the chloride. The orbital requirements for an SN2 reaction are not met with a carboxylic acid derivative. And sometimes a proton transfer will be necessary in the mechanism. And it's important to remember that if you're in acidic conditions, you want to avoid forming negative charges. And if you're in basic conditions, avoid forming positive charges. So here's an example of an ester reacting with water and acid to form a carboxylic acid. This is an example of a hydrolysis reaction. Since this is an acid, the first step is not going to be nucleophilic attack because then you would create a negative charge on the oxygen. So with acidic conditions instead, you want the first step to be protonation of that carbonyl oxygen to form this intermediate. And protonation is generally always the first step in an acyl substitution mechanism under acidic conditions. Now once you've protonated the carbonyl, now water can do the nucleophilic attack to form this new intermediate. And here you're avoiding forming those negative charges in acidic conditions. Now, if instead we were under basic conditions, then it's okay to form negative charges and we want to avoid forming positive charges. So here we could have nucleophilic attack be first. So that will be first. Then we get to that intermediate. And notice we're in base and we haven't formed positive charge, which is good. When an amine is the nucleophile, it's a very good nucleophile. It will always attack the carbonyl first without the carbonyl being protonated first. So whenever you have an amine as the nucleophile, go ahead and show it attacking the carbonyl carbon first without protonation occurring. And if you think back to the imine and the enamine mechanisms, that's what you drew in your first step. You didn't protonate the carbonyl first, even though there was catalytic acid. You had the amine attack first. Proton transfers are utilized in mechanisms to remain consistent with whatever the conditions are that are employed. And with acidic conditions, often up to 3 proton transfers are necessary. And you will have to figure out if the conditions are acidic, neutral, or basic to determine and decide where these proton transfers should occur in the mechanism. So consider the mechanism for the hydrolysis of an acid chloride. So in this set of conditions, you have an acid chloride and you're reacting it with water. There's no acid over the arrow, so this is not in acidic conditions. So the first thing you would do is do nucleophilic attack because we're not in acid. So the water is going to attack the carbonyl carbon, and then we're going to lose a leaving group. So that reforms the carbonyl and kicks off the chloride. And then finally, you can do a proton transfer at the end because we want to end up with a product that's not charged. So water is going to grab this hydrogen and form the carboxylic acid product. Now note here that the leaving group, the chloride, did not require protonation in order to leave, but there is a proton transfer at the very end. An acid chloride can be made from a carboxylic acid using thionyl chloride, SOCl2, shown here. And in this mechanism, the first step is that we're going to have the carboxylic acid be the nucleophile, and it's going to attack the thionyl chloride. So we can show a lone pair forming a double bond, and this pi bond breaking, attacking the very electrophilic sulfur, breaking that pi bond. So that's 3 curved arrows. Then we get to this intermediate, which is going to collapse and kick off chloride. So now we have loss of a leaving group. Then the chloride that we kicked off can come back in and do a proton transfer to get to here. So now this portion of the molecule in green is an excellent leaving group. So the whole point of this was to transform the OH essentially of the carboxylic acid into a great leaving group. So we have this intermediate from the previous slide, and now chloride can come in and do a nucleophilic attack to form this intermediate, which can then collapse and kick off that entire leaving group to form the acid chloride, and then this side product collapses to form SO2 and chloride. And this is an animation of that reaction. So here we have the oxygen attacking the thionyl chloride. It kicks off the chloride. Now we have the Cl- that was kicked off, grabbing a proton. Now we have another chloride coming in, attacking the carbonyl carbon to form that tetrahedral intermediate, which then collapses, kicking off SO2 and chloride. When reacted with water, an acid chloride is converted into a carboxylic acid. So in this, the first step is the water performs a nucleophilic attack, and then you get to that tetrahedral intermediate, which then collapses and kicks off chloride as the leaving group. And then you get a proton transfer to get to your carboxylic acid product. Here is an animation of the hydrolysis of an acid chloride. So there water is attacking, and now the proton transfer can occur. And then you're going to kick off chloride as the leaving group. So you may have noticed here that in this animation, the proton transfer occurred first before the leaving group left, whereas in the last slide, I had those steps switched. So in practice, you could write the mechanism either way, with the proton transfer as the second step or as the last step. Since HCl is a byproduct of hydrolysis, we often add a base like pyridine, which is this structure. It's essentially benzene with a nitrogen in it to neutralize the HCl that's formed. Acid chlorides react with an alcohol to make an ester. So here we have the acid chloride, and the part shown in red gets attached to this oxygen of the alcohol to form this ester. Sterically hindered alcohols react more slowly. So, for example, a primary alcohol could be converted selectively in the presence of a secondary alcohol to an ester. So here we have a secondary alcohol and a primary So if we react this with one equivalent of this acetyl chloride, we can esterify that primary alcohol selectively. So notice all of these carbons are now attached to the oxygen of that primary alcohol. And acid chlorides can be used to make amides. So if you want a primary amide, you would use ammonia NH3. If you wanted a secondary amide, you would use RNH2. And if you wanted a nitrogen with two R groups, you would use a secondary amine. And notice in all of these, we're going to use two equivalents of the amine. Acid chlorides can also be reduced using lithium aluminum hydride to form a primary alcohol. So in this reaction, the hydride is going to add 2 times. So the first time the hydride adds, you form the tetrahedral intermediate, which collapses to kick off chloride. So here we're removing chloride as the leaving group, and we get to an aldehyde intermediate. So then the hydride adds a second time, and that's how we get our 2 hydrogens added. And with the acidic workup or the acid workup, we end up protonating the O- to get to the alcohol product. If we use a less reactive hydride like lithium tri-T-butoxy aluminum hydride, you can actually stop this reduction at the aldehyde stage. An acid chloride can be reacted with a Grignard to form a tertiary alcohol. So here, this is like what you've seen before with Grignards and esters. The R group simply is going to add twice. So first it adds in, attacks the carbonyl carbon. You form the tetrahedral intermediate, which collapses, kicking off chloride, and now you have a ketone. And then the R group adds a second time, and after a water workup step and a proton transfer, we get our tertiary alcohol. There's something called a Gilman reagent, which is a cuprate reagent. It has R groups attached to a copper atom, and this can add to an acid chloride to form the ketone. So whatever the R group here is of the Gilman replaces the chloride of the acid chloride. So this is an overview. This is like a mini concept map of all of the different types of reactions of acid chlorides. So with water, you can convert it to the carboxylic acid. From a carboxylic acid, you can form the acid chloride with thionyl chloride. You can convert it to a ketone using the Gilman, a tertiary alcohol using Grignard. With the more selective hydride reagent, the trialkoxy reagent, you can stop the aldehyde. But with just normal lithium aluminum hydride, you get hydride addition twice to get to the primary alcohol. You can use a variety of different amines to get to these variety of different amides, and you can use alcohol to get to an ester. So notice with this, there are ways to convert an acid chloride to the less reactive derivatives, as well as converting it to other things such as ketones, alcohols, and a carboxylic acid. Now let's switch gears to anhydrides. Anhydrides can be synthesized by excessive heating of a carboxylic acid, but this typically only works for acetic acid, and look at the temperature required, 800 degrees Celsius. So most acids cannot survive such an extreme temperature. So for a practical synthesis of anhydrides, we're going to use the very reactive acid chloride and add a carboxylate. So in this case, the carboxylate is the nucleophile. It attacks the carbonyl carbon. You form this intermediate, which collapses and kicks off your chloride leaving group, and you get your anhydride product. Acid anhydrides react in a way that's directly analogous to acid chlorides. So with all the acid chloride reactions, the Cl was the leaving group. With anhydride reactions, this entire portion of the molecule will act as the leaving group. So you could do all of the same types of things with acid anhydrides that we saw with acid chlorides. So you can take an acid anhydride to an ester using an alcohol. You can react it with various amines to get to various amides. You can use excess lithium aluminum hydride to get to a primary alcohol. You can use that more selective trialkoxy hydride to get to the aldehyde. You can use excess Grignard to get to a tertiary alcohol, or you can use the Gilman to get to a ketone. To form the carboxylic acid, you would also use water, just like with acid chloride. To form the anhydride, you can take a carboxylic acid and form a carboxylate, then react that with the acid chloride. And all of the mechanisms for all of these are directly analogous to the mechanisms with acid chlorides. Here is an animation of hydrolysis of an anhydride. So the water's nucleophile, it's attacking, forming the tetrahedral intermediate, which is then going to undergo a proton transfer. And now the tetrahedral intermediate collapses, kicking off the right-hand portion of the molecule, just like we kicked off chloride with the hydrolysis of acid chlorides. So anhydrides with an alcohol make esters, with amines they make amides. And in particular, acetic anhydride, which is this structure, is often used to put an acetyl group, which is a carbonyl with a methyl attached, onto an oxygen or a nitrogen. Indeed, acetic anhydride is used commercially to synthesize aspirin and Tylenol. So this is aspirin, and we can use acetic anhydride to acylate the phenol OH group or to acylate the amino group to form Tylenol. So let's finish up with some questions. Provide the correct IUPAC name for the following structure. So this is an ester functional group, so look back to your ester naming rules. So here we have an acid chloride. Provide the correct name for this. Here is a reaction between an acid chloride and a carboxylate. Predict the product of this reaction. Finally, this is a two-step problem. So what is the final product of the following reaction? So this carboxylic acid will react with thionyl chloride to form something, which will then go on to react with ethanol to form something. So what is the final product here following those two steps? Put your answer in the chat.